Hello, this is Mr. Craig, and this is, I believe, period 7's 20 to make 12 quiz. The first questions 1 through 4 refer to the experiment in which 5 individual 1 liter aqueous solutions, each containing 1 mole of one of the salts listed below, were subjected to various tests at room temperatures. So what this is saying is that each of these are a 1 molar solution. Okay. Question number 1 says the solution containing this salt had the highest boiling point. When we talk about boiling point, we're looking at an equation, and again, you don't have the equation sheet in front of you, but we're looking at this equation here where we have Van Hoff factor times the constant for the boiling point times the molality. Now, for all these situations, the molality happens to be the same because you have 1 mole in a 1 liter solution, which also equates to, since we're using water, as a 1 kilogram. So all of them have the same molality. All of these have the same Kb, or the constant. So the only difference for all these salts is the Van Hoff factor, or simply how many particles does it dissociate into once it's been placed into the solvent, or in this case, the water. So when we look at sodium acetate will actually dissociate into sodium ions and acetate ions. So our Van Hoff factor for sodium acetate is 2. Sodium chloride does something very, very similar, and it has the same effectiveness as sodium acetate because it has 2 particles as well. So even though we have this big, huge, complex carbon compound or organic compound, it doesn't have any more power or potential to cause the boiling point to go up or down because it only counts as 1 particle. So it's not the size of the particle, it's actually how many particles that will either raise or lower the boiling point or freezing point, respectively. Looking at the magnesium bromide, magnesium has a +2 charge, doesn't matter, but the 2 bromines that actually dissociated from that do matter, so we have a total of 3. So our Van Hoff factor just took over on that one, so these guys are definitely out for number 1. D is a weak acid. So the Van Hoff factor is at least 1, but it definitely is not 2. Even though we don't ever work with Van Hoff factors for weak acids, this one might be 1.1. It's hard to say. Unless you were given that value, it's very, very difficult to predict. So some of the hydrogens will dissociate from the acetate, but they all will not dissociate. And the potassium bromide, we have another Van Hoff factor of 2. So the correct answer for number 1 is C. All right, let me clear that off. All right, looking at number 2, the solution containing this salt had the lowest conductivity. When we talk about conductivity of ionic compounds, the more particles we have, the greater the conductivity. However, the fewer the particles we have, ionic particles that we have, doesn't allow for the electrons to move easily from ion to ion. Even though the acetic acid does dissociate somewhat and has a very, very low Ka. Actually, it's not very, very low. It's actually a Ka value, and you don't have to memorize this, of 1.8 times 10 to the negative 5. If we look at all the other salts that are on here, they have KSPs that are well above 1. So the thing that we want to look at on a problem like this is look for the thing that's most molecular. In other words, the thing that doesn't produce as many ions. And that is your winner. So for number 2, it should be D. All right, number 3, the solution containing this salt had the highest pH. When we talk about pH, again, highest pH means that we're looking at a basic solution. Well, we know that this is an acidic solution, so we can cancel that one out. Then we have to start looking at other things to see how they're going to form OH. Now, here's the really crazy thing is none of these things have hydroxide within them. So we can't use that to help us determine which one's going to cause for a high pH. However, if you see questions like this, I guarantee you they're going to give you your acid and its conjugate salt. And that's really cool because if we look at the acetate ion, we have a common ion within that salt. So we know that this is going to behave like an acid, but what is this going to do? Well, we know that the sodium is going to dissociate from it. And what will sodium do? Well, unfortunately, nothing, because it's conjugate of a strong base, so the sodium will do nothing. However, this acetate acts like a conjugate of a weak acid, so it behaves as a base. And here's what actually happens. When the acetate ion reacts with water, it actually rips a hydrogen off of the water to form the H2CH3, the acetic acid, and most importantly, hydroxide ions. And when we form those hydroxide ions, we're adding more hydroxide to the solution, increasing the pOH, which causes the pH to go up. So our best answer here is A. That will be the only one, actually, of all of these that actually form any basic solution here. All right, number 4. The solution containing this salt had the lowest vapor pressure. Again, going back to the Van Hoff factor, if we have something with a high boiling point, then the vapor pressure has a low value. Now, what is vapor pressure? Vapor pressure, again, is the ability for the liquid to change into a gas. So in other words, if we're looking at something that's volatile, or like acetone, gasoline, when I open this container up, I smell it immediately. The reason why I smell it immediately is because it has a high vapor pressure. Well, what does that mean about the boiling point? That means that the boiling point is really low. So if the boiling point is low, the vapor pressure is high. It's an inverse proportionality. If I have something with a high boiling point at room temperature, I'm not going to see too many vapors above it. Okay? But once I get that substance like steam or water, if I boil water and I get it to boil, now my vapor pressure is actually equal to the atmospheric pressure. And what that's saying is, at the boiling point, all that gas above is equal to the external pressure. That's why that liquid's boiling. So I've given enough energy so that the external pressure can't do anything to help it stay as a liquid. However, so get back to answer the question, which of these has the highest vapor pressure? Well, whatever one of these has the lowest Van Hoff factor. And the one that has the lowest not the lowest, has the highest Van Hoff factor, because again, higher boiling point, lower vapor pressure. So C, again, is our answer for number 4. And again, when we talk about vapor pressure, we really want to look at a couple considerations. What is the temperature of the solution, if we know the boiling point? Also, how many particles do we have in that solution? Because we can elevate the boiling point if we add stuff to it, as long as the Van Hoff factor is high enough on that. All right, number 5. If 1 Faraday is equivalent to 96,000 coulombs per mole of electrons, how many Faradays are required for the reaction of 1 mole of sodium ions to go to solid sodium? Well, here's the question you have to ask yourself. How many moles of electrons are needed to go from sodium with a +1 to solid sodium? Well, we need 1 mole of electrons, which means that we need 1 Faraday. Don't pick this. I know way too many students that read that and say, oh yeah, 1 Faraday is equal to that. It's asking for how many Faradays. Okay? This is your conversion. 1 Faraday is that. We need 1. So don't pick 96,000 Faradays. We don't have that many electrons to play with here. Read the question carefully is what this is saying. All right, number 6. Methane gas reacts with oxygen gas to produce carbon dioxide and water. All gases. What volume of oxygen at STP is reacted with 16 grams of methane? All right, we have a stoichiometry problem. We have what appears to be a calculator type problem, but we don't need a calculator for this. So first of all, stoichiometry, step 1, write a balanced equation. So methane, write all of our reactants down, and produces carbon dioxide and water. Okay. So balance this out. So we have 4 hydrogens, so we need a 2 there. Carbons are good, so it looks like we're ready to roll. So 2 oxygen plus 2 more. So we have that. All right, so we have our balanced equation. And again, as a heads up here, whenever balancing combustion reactions, save the oxygen for last when balancing. Also, try to make this an even coefficient. Okay, say like if we had a 6 here for our hydrogen count, you wouldn't want to put a 3 there. If you put a 3 there, that gives you an odd number of oxygen. So just double that and make it a 6, if that were a 6. Okay, so make it two real quick steps. Make the make the value in front of water even, and save the oxygen for last. It's just a real quick step that I teach my general chem kids, and it'll save you a lot of time as well. All right, so stoichiometry, step 1's done. Step 2, change what's given. So we have 16 grams of methane. Change what's given into moles. So change grams into moles. Now again, you don't get a periodic table for this, so estimate. Carbon, approximately 12. Hydrogen, approximately 1. So that gives me 16 grams. How nice, that's 1 mole. All right, so step 2's done, converting the grams into moles. Step 3, use the mole ratio. I have 1 mole of methane. And the question wants to know, what is the volume of oxygen? So I need to compare that to oxygen. So my coefficient for there goes in my mole ratio. So I got rid of the units I started with. Now I have moles of oxygen. So that's step 3. Step 4, convert it back to the desired unit, and it wants to know what is volume. Since we're at STP, 1 mole of oxygen has a volume of 22.4 liters. Make sure you know that. So here's the math. 16 divided by 16 is 1. Times 2 is 2. 2 times 22.4, 44.8. Okay. Now, yes, this problem may take more than 1.2 minutes to answer, but please, this would be one that I might circle and say I need to come back to this one. Okay. This is one that we all should be able to answer, but it may be a little time consuming. So don't make this a mission. All right. Number 7, which anion, non-metal, that's what anion means, forms the greatest number of insoluble salts. Insoluble means, essentially, forms a lot of precipitates. So, right off the bat, make sure you know your solubility rules. Nitrates, chlorates, acetates, very soluble. Chlorine, yeah, with silver and lead, but phosphate does not like to dance with anybody. So B's your best choice here. And again, it's all about knowing your solubility rules. Number 8, which piece of apparatus can measure a volume of 25 milliliters most precisely or most accurately? Typically, we do not use beakers to measure things out in. Don't do that. Yes, it does have some volume markings on there, but it's approximate. Conical flask or an Erlenmeyer flask, I put that in the same category as a beaker. Don't use that. Graduated cylinder, not bad. Let's jump down to crucible. Crucible is like a ceramic pot, so there's no measuring going on with a crucible. Now pipettes are pretty darn accurate. What they are these glass tubes or plastic tubes, and they have typically like 1/10 of a millimeter, or even some are a little more accurate, some are a little less accurate. But compared to a graduated cylinders typically go 1 milliliter, maybe 2 milliliters, but pipettes definitely more accurate. Okay, so in this one, I would definitely pick the pipette for my answer on this one. Okay. All right. I don't know where the answer is. Oh, there it is, D. Okay, number 9. Acetylene reacts with oxygen according to the unbalanced equation. Okay, and the question wants to know, what is the oxygen to acetylene ratio when this equation is correctly balanced? So, we got to balance it. All right, so we have, let's see, 2 carbons, 1 carbon, 2 hydrogen, 2 hydrogen. So that one looks good, but we have 2 carbons here, so we need to balance that. So now, let's see. Yeah, okay, oxygen. Oh, here we go. We have 5 oxygen, so we need to get an even number over here. So let's put a 2 there, which means I need to have a 2 in front of there, so that one goes to a 4. All right, so now we have 8 plus 2, so 5. All right, so now that we have our balanced equation, we have a 5-to-2 ratio, and whichever answer that one is. Looks like D. Okay. So again, this should be a type of question that should be answered rather quickly. Just bounce the equation out. And again, notice what I did here. Make sure that you have an even number of waters here to help things out, especially if you have oxygen, O2, have an even number of oxygen on the left side, we have to have an even number of oxygen on the right. All right, number 10. Which diatomic molecule has the shortest bond length? Generally speaking, when we look at single bonds, they're the longest. Double bonds, they're the middle. Triple bonds are actually the shortest length. Now, here's one real quick way to remember, especially when dealing with formal charges. If you have your noble gases, group 8A, and then we have our group 7A, which starts off with fluorine at the top, group 6A, which is oxygen, group 5A, which has nitrogen up there. Group 7A wants to be single bonded. Group 6A, nonmetals want to be double bonded. Group 5A, nonmetals want to be triple bonded. So, triple, double, single, double, single. Now again, hydrogen, we know, can only have 2 electrons. So the best choice on this one would be nitrogen. Make sure that you can do formal charges. Make sure that you can draw these structures rather quickly. And be sure that you know this rule here, single, double, triple. And especially as external atoms, that's what those want to be. So, and we know that those actually follow suit as well for sharing of electrons, drawing those structures. All right, number 11. The only substance listed below that contains ionic, sigma bonds, and pi bonds. Now, if we have an ionic bond and we have sigma and pi, then we have to have a polyatomic ion somewhere in there. There's only one choice right here. Now, be sure that you know what sigma and pi represents. A sigma bond is a single bond. A sigma pi is a double bond. A sigma pi is a triple bond. Okay. Make sure that you know that. So if you were asked, okay, here we have a situation where we have oxygen, carbons, and some hydrogens. And you'll be asked this, I promise, either on question 6 of the free response or somewhere in the multiple choice. You're given this compound, and hopefully it's already drawn for you, or you have to draw it. That's a sigma there, and pi. So the question wants to know, how many sigma bonds do we have on this structure? Well, remember that a double bond has 1 sigma and 1 pi, so there's 2 sigma there, 3, 4, 5, 6, 7, 8. 8 sigmas, and there's 2 pi there. Okay? So be sure that you can determine how many sigma and how many pi. This question doesn't ask that. It just asks which contains ionic, sigma, and pi bonds. All right, number 12. A student wishes to determine the thickness of a rectangular piece of aluminum foil but cannot measure it directly. She can measure its density, its length, its mass, and its width. What relationship will give the thickness? Now, thickness, in my opinion, means height. So when we talk about density, first and foremost, we're looking at mass over volume, which could be written as mass over length times width times height or thickness. Okay? So we can ignore that for right now. So that equals density. Okay? So what we have to realize is if we're looking for the thickness or the height, we're looking for that. So we know that. So let's switch these two. So now, when we look at our equation, we have H here and D is down here. So that one's the inverse of the answer. That is nothing. And these, yeah. So A should be our correct answer. Again, don't need a calculator to answer these. All right, number 13, electron configuration represented all the following except. So we're looking for a 5th energy level element here. So So xenon. So we're looking for something that is isoelectronic with xenon. All right, so we've got iodine. Yep. Antimony. I believe I saw that over there. Antimony and tellurium. I believe they're neighbors. Yep, so they're in there. So those are isoelectronic. And then I thought I saw rubidium. So rubidium will not be isoelectronic here. So that one's the answer. B, not isoelectronic with that. Okay, and be sure that you can do that by looking at the periodic table quickly. Be sure you know what isoelectronic means. Well, the same electron configuration as its nearest noble gas. And we'll always be looking at charges associated with that. All right, 14, which is not a conjugate acid-base pair. So when we talk about conjugate acids and bases, probably the simplest way to do this is here's my acid, because it has a hydrogen in front, and we could react it with something. Most often we can react it with water. And then what's the acid doing? Well, it's giving a hydrogen to the base. So there's my acid, there's my base. So on the other side, I'm going to have an anion plus H3O plus, and for it to get back to this, then it has to donate a hydrogen as well. So if my acid gave away its hydrogen, it's now considered a conjugate base. For my conjugate acid to get back to the way it is as a base, it needs to give away that hydrogen. So when you see a question like this, conjugate acid-base pair, don't worry about who's the acid, who's the base. Ask yourself this: which one has one less hydrogen? If it has one less hydrogen, then we have an acid-base pair, or conjugate acid-base pair. So looking at the first one, we have two hydrogens, no hydrogens there. That's a difference of two hydrogens. That's huge. That's our answer. Here, B, I have one hydrogen, no hydrogens, difference of one hydrogen. Here I have two hydrogens, one hydrogen, difference of one hydrogen. Here I have three hydrogens, two hydrogens, difference of one hydrogen. Here I have one hydrogen, no hydrogens, difference of one hydrogen. These are all, B through E, are conjugate acid-base pairs. So A is the best choice. All right, number 15. Okay. We have a redox problem here. It says balance to half reaction for an acidic solution, and again, key point there, acidic solution, using the smallest whole number or possible whole number coefficients and entering the proper number of electrons where needed. All right, so whenever balancing out redox equations, make sure you balance your non-oxygen, non-hydrogen elements first. So we have to start off with the thing that has the OS for the osmium. So OS2, O5, -2 goes to osmium, but we need two of those, so we have a 2 there. OS plus 2. All right, so we have our non-oxygen, non-hydrogens balanced. Next thing that we need to do is balance the number of oxygens. The way we do that, again, it's a solution that's acidic. We add water molecules. So we'll add 5 water molecules. Why? Because I need 5 oxygens. So that gives me my 5 oxygens. And then I have my osmiums and my oxygens balanced. So now I have to balance hydrogen. And since we have an acidic solution, that means we have a bunch of hydrogen ions in solution. I have 5 times 2, which is 10 hydrogen ions. Okay. And then, now that I have all my atoms balanced, I have to balance charges. So on the right side, I have 2 times a plus 2. That's a plus 4. Over here, I have plus 10 minus 2, which is a plus 8. So to get the same charges, I need to add electrons. That's my final step. And in this case, I'd add 4 electrons to balance that out. D. Be sure you can do redox. If you don't remember how to do redox equations, I highly advise you to go back and review that. Very, very important. All right. Number 16 from question 5, the hydrogen ions. We had 10 on the left, so whatever one is 10 on the left. So E for number 16. Okay. 17. What is the pH of a 0.001 mole solution of potassium hydroxide? The bad news is when you read this question, your brain does funny things. you're sitting here and you're going, oh, I can do that in my head. I can do negative log of 0.001, which equals 3. pH is 3. No. Why is the pH not 3? Because we're looking at a basic solution. So if your concentration for the potassium hydroxide is that, we just calculated the pOH. So to find the pH, we need to take pH, which is equal to 14 minus pOH, and we just calculated it to be 3, so our pH is actually 11. Be very, very careful when doing these types of problems. The brain does some crazy things when you see a question like this. I know that a lot of you are able to do logs in your head, and you should be able to. In other words, for example, if I were to give you, say, a concentration of like 0.005, you should be able to predict what the range in the pH is. Now, we know that if we had a 1 there, that would be a 3. But also ask yourself, what is 0.005 between? Well, it is between 0.01 and 0.001. So since it's in that range, this represents 3, this represents 2. So our value should be somewhere between 2 and 3. You don't have to have a definite value there, but you should be able to predict what it is close to. Also, make sure that if you have log values, that are like greater than 1, then you know that your value should have a positive value. If you have a log value that is less than 1, okay, then our log value should be negative. That really plays an important part when we do electrochemistry stuff with the Nernst equation. And I'll try to put that in some future questions here, future quizzes. But again, know your basics in log base 10. All right, number 18. How many half-lives have elapsed if 87.5% of the parent nuclei have reacted to form daughter nuclei? So in other words, what we are looking for is 87.5 of that has reacted. So really, we only have 12.5% remaining. So you have to ask yourself, okay, how many half-lives have I gone through? Well, if I start off with 100% and I go through one half-life, I'm now down to 50. If I go another half-life, I'm now down to 25. If I go through another half-life, I'm now down to 12.5. 3 half-lives. Okay? Half-lives, easy points, guys. Easy, easy points. Just slow down, read the question. Number 19. Which element has an outer electron configuration of S2P4? So what we need to do is go to our periodic table. Which elements have 6 valence electrons? So it's either oxygen, sulfur, selenium, tellurium, polonium. Okay, I know. There is no energy levels on there. Don't freak out on that. This is telling you that this thing has 6 valence electrons. That's all it's saying. Okay, number 20. Which species is nonpolar? If you're not sure, draw the Lewis structures. Hopefully you can recognize real quickly that carbon tetrachloride is nonpolar. How do we know that? Carbon always wants to have 4 bonds, and if all my external atoms are the same and there's no lone pairs on the central atom, this is always nonpolar. Very polar. Polar, polar, polar. I hope this quiz has helped. Look for some more videos coming up here. These things are fun to make, but they are time consuming. But if it helps you get a good score on the AP exam, I am all for doing this. I hope this has helped.